If the alternator output frequency varies from 400 Hz, the APU speed control adjusts the engine RPM accordingly to keep the alternator output within limits. AC alternators control systems. Modern aircraft that employ AC alternators use several computerized control units, typically located in the aircraft's equipment bay for the regulation of AC power throughout the aircraft. Figure 9.81 shows a photo of a typical equipment bay and computerized control units. Since AC alternators are found on large transport category aircraft designed to carry hundreds of passengers, their control systems always have redundant computers that provide safety in the event of a system failure. Unlike DC systems, AC systems must ensure that the output frequency of the alternator stays within limits. If the frequency of an alternator varies from 400 Hz, or if two or more alternators connected to the same bus are out of phase, damage occurs to the system. All AC alternator control units contain circuitry that regulates both voltage and frequency. These control units also monitor a variety of factors to detect any system failures and take protective measures to ensure the integrity of the electrical system. The two most common units used to control AC alternators are the Bus Power Control Unit, BPCU, and the Generator Control Unit, GCU. In this case, the term generator is used, and not alternator, although the meaning is the same. The GCU is the main computer that controls alternator functions. The BPCU is the computer that controls the distribution of AC power to the power distribution buses located throughout the aircraft. There is typically one GCU used to monitor and control each AC alternator, and there can be one or more BPCUs on the aircraft. BPCUs are described later in this chapter, however, please note that the BPCU works in conjunction with the GCUs to control AC on modern aircraft. End of page 9-44. A typical GCU ensures the AC alternator maintains a constant voltage, typically between 115 to 120 volts. The GCU ensures the maximum power output of the alternator is never exceeded. The GCU provides fault detection and circuit protection in the event of an alternator failure. The GCU monitors AC frequency and ensures the output if the alternator remains 400 Hz. The basic method of voltage regulation is similar to that found in all alternator systems. The output of the alternator is controlled by changing the strength of a magnetic field, as shown in Figure 9.82. The GCU controls the exciter field magnetism within the brushless alternator to control alternator output voltage. The frequency is controlled by the CDS hydraulic unit in conjunction with signals monitored by the GCU. The GCU is also used to turn the AC alternator on or off. When the pilot selects the operation of an AC alternator, the GCU monitors the alternator's output to ensure voltage and frequency are within limits. If the GCU is satisfied with the alternator's output, the GCU sends a signal to an electrical contactor that connects the alternator to the appropriate AC distribution bus. The contactor, often called a generator breaker, is basically an electromagnetic solenoid that controls a set of large contact points. The large contact points are necessary in order to handle the large amounts of current produced by most AC alternators. This same contactor is activated in the event the GCU detects a fault in the alternator output. However, in this case the contactor would disconnect the alternator from the bus. End of page 9-45. Aircraft electrical systems. Virtually all aircraft contain some form of an electrical system. The most basic aircraft must produce electricity for operation of the engine's ignition system. Modern aircraft have complex electrical systems that control almost every aspect of flight. In general, electrical systems can be divided into different categories according to the function of the system. Common systems include lighting, engine starting, and power generation. Small single-engine aircraft. Light aircraft typically have a relatively simple electrical system because simple aircraft generally require less redundancy and less complexity than larger transport category aircraft. On most light aircraft, there is only one electrical system powered by the engine-driven alternator or generator. The aircraft battery is used for emergency power and engine starting. Electrical power is typically distributed through one or more common points known as an electrical bus or bus bar. Almost all electrical circuits must be protected from faults that can occur in the system. Faults are commonly known as opens or shorts. An open circuit is an electrical fault that occurs when a circuit becomes disconnected. A short circuit is an electrical fault that occurs when one or more circuits create an unwanted connection. The most dangerous short circuit occurs when a positive wire creates an unwanted connection to a negative connection or ground. This is typically called a short to ground. There are two ways to protect electrical systems from faults, mechanically and electrically. Mechanically, wires and components are protected from abrasion and excess wear through proper installation and by adding protective covers and shields. Electrically, wires can be protected using circuit breakers and fuses. The circuit breakers protect each system in the event of a short circuit. It should be noted that fuses can be used instead of circuit breakers. Fuses are typically found on older aircraft. A circuit breaker panel from a light aircraft is shown in Figure 9.83. Battery circuit. The aircraft battery and battery circuit is used to supply power for engines starting and to provide a secondary power supply in the event of an alternator or generator failure. A schematic of a typical battery circuit is shown in Figure 9.84. This diagram shows the relationship of the starter and external power circuits that are discussed later in this chapter. The bold lines found on the diagram represent large wire. See the wire leaving the battery positive connection, which is used in the battery circuit due to the heavy current provided through these wires. Because batteries can supply large current flows, a battery is typically connected to the system through an electrical solenoid. At the start/end of each flight, the battery is connected/disconnected from the electrical distribution bus through the solenoid contacts. A battery master switch on the flight deck is used to control the solenoid. Although they are very similar, there is often confusion between the terms solenoid and relay. A solenoid is typically used for switching high current circuits and relays are used to control lower current circuits. To help illuminate the confusion, the term contactor is often used when describing a magnetically operated switch. For general purposes, an aircraft technician may consider the terms relay, solenoid, and contactor synonymous. Each of these three terms may be used on diagrams and schematics to describe electrical switches controlled by an electromagnet. Here it can be seen that the battery positive wire is connected to the electrical bus when the battery master switch is active. A battery solenoid is shown in Figure 9.85. The battery switch is often referred to as the master switch since it turns off or on virtually all electrical power by controlling the battery connection. Note how the electrical connections of the battery solenoid are protected from electrical shorts by rubber covers at the end of each wire. The ammeter shown in the battery circuit is used to monitor the current flow from the battery to the distribution bus. When all systems are operating properly, battery current should flow from the main bus to the battery, giving a positive indication on the ammeter. In this case, the battery is being charged. If the aircraft alternator or generator experiences a malfunction, the ammeter indicates a negative value. A negative indication means current is leaving the battery to power any electrical load connected to the bus. End of page 9-46. The battery is being discharged and the aircraft is in danger of losing all electrical power. Generator circuit. Generator circuits are used to control electrical power between the aircraft generator and the distribution bus. Typically, these circuits are found on older aircraft that have not upgraded to an alternator. Generator circuits control power to the field winding and electrical power from the generator to the electrical bus. A generator master switch is used to turn on the generator, typically by controlling field current. If the generator is spinning and current is sent to the field circuit, the generator produces electrical power. The power output of the generator is controlled through the generator control unit, or voltage regulator. A simplified generator control circuit is shown in Figure 9.86. As can be seen in Figure 9.86, the generator switch controls the power to the generator field, F terminal. The generator output current is supplied to the aircraft bus through the armature circuit, a terminal, of the generator. Alternator circuit. Alternator circuits, like generator circuits, must control power both to and from the alternator. The alternator is controlled by the pilot through the alternator master switch. The alternator master switch in turn operates a circuit within the alternator control unit, or voltage regulator, and sends current to the alternator field. If the alternator is powered by the aircraft engine, the alternator produces electrical power for the aircraft electrical loads. The alternator control circuit contains the three major components of the alternator circuit: alternator, voltage regulator, and alternator master switch. Figure 9.87. The voltage regulator controls the generator field current according to aircraft electrical load, alternator. If the aircraft engine is running and the alternator master switch is on, the voltage regulator adjusts current to the alternator field as needed. End of page 9 to 47. If more current flows to the alternator field, the alternator output increases and feeds the aircraft loads through the distribution bus. All alternators must be monitored for correct output. Most light aircraft employ an ammeter to monitor alternator output. Figure 9.88 shows a typical ammeter circuit used to monitor alternator output. An ammeter placed in the alternator circuit is a single polarity meter that shows current flow in only one direction. This flow is from the alternator to the bus. Since the alternator contains diodes in the armature circuit, current cannot reverse flow from the bus to the alternator. When troubleshooting an alternator system, be sure to monitor the aircraft ammeter. If the alternator system is inoperative, the ammeter gives a zero indication. In this case, the battery is being discharged. A voltmeter is also a valuable tool when troubleshooting an alternator system. The voltmeter should be installed in the electrical system while the engine is running and the alternator operating. A system operating normally produces a voltage within the specified limits, approximately 14 volts or 28 volts depending on the electrical system. Consult the aircraft manual and verify the system voltage is correct. If the voltage is below specified values, the charging system should be inspected. External power circuit. Many aircraft employ an external power circuit that provides a means of connecting electrical power from a ground source to the aircraft. External power is often used for starting the engine or maintenance activities on the aircraft. This type of system allows operation of various electrical systems without discharging the battery. The external power systems typically consists of an electrical plug located in a convenient area of the fuselage, an electrical solenoid used to connect external power to the bus, and the related wiring for the system. A common external power receptacle is shown in Figure 9.89. Figure 9.90 shows how the external power receptacle connects to the external power solenoid through a reverse polarity diode. This diode is used to prevent any accidental connection in the event the external power supply has the incorrect polarity, i.e., a reverse of the positive and negative electrical connections. End of page 9 to 48. A reverse polarity connection could be catastrophic to the aircraft's electrical system. If a ground power source with a reverse polarity is connected, the diode blocks current and the external power solenoid does not close. This diagram also shows that external power can be used to charge the aircraft battery or power the aircraft electrical loads. For external power to start the aircraft engine or power electrical loads, the battery master switch must be closed. Starter circuit. Virtually all modern aircraft employ an electric motor to start the aircraft engine. Since starting the engine requires several horsepower, the starter motor can often draw 100 or more amperes. For this reason, all starter motors are controlled through a solenoid. Figure 9.91. The starter circuit must be connected as close as practical to the battery since large wire is needed to power the starter motor, and weight savings can be achieved when the battery and the starter are installed close to each other in the aircraft. As shown in the starter circuit diagram, the start switch can be part of a multifunction switch that is also used to control the engine magnetos. Figure 9.92. The starter can be powered by either the aircraft battery or the external power supply. Often when the aircraft battery is weak or in need of charging, the external power circuit is used to power the starter. During most typical operations, the starter is powered by the aircraft battery. The battery master must be on and the master solenoid closed in order to start the engine with the battery. Avionics power circuit. Many aircraft contain a separate power distribution bus specifically for electronics equipment. This bus is often referred to as an avionics bus. Since modern avionics equipment employs sensitive electronic circuits, it is often advantageous to disconnect all avionics from electrical power to protect their circuits. For example, the avionics bus is often depowered when the starter motor is activated. This helps to prevent any transient voltage spikes produced by the starter from entering the sensitive avionics. Figure 9.93. End of page 9 to 49. The circuit employs a normally closed NC solenoid that connects the avionics bus to the main power bus. The electromagnet of the solenoid is activated whenever the starter is engaged. Current is sent from the starter switch through diode D1, causing the solenoid to open and depower the avionics bus. At that time, all electronics connected to the avionics bus will lose power. The avionics contactor is also activated whenever external power is connected to the aircraft. In this case, current travels through diodes D2 and D3 to the avionics bus contactor. A separate avionics power switch may also be used to disconnect the entire avionics bus. A typical avionics power switch is shown wired in series with the avionics power bus. In some cases, this switch is combined with a circuit breaker and performs two functions, called a circuit breaker switch. It should also be noted that the avionics contactor is often referred to as a split bus relay, since the contactor splits, the avionics bus from the main bus. Landing gear circuit. Another common circuit found on light aircraft operates the retractable landing gear systems on high-performance light aircraft. End of page 9 to 50. These airplanes typically employ a hydraulic system to move the gear. After takeoff, the pilot moves the gear position switch to the retract position, starting an electric motor. The motor operates a hydraulic pump, and the hydraulic system moves the landing gear. To ensure correct operation of the system, the landing gear electrical system is relatively complex. The electrical system must detect the position of each gear, right, left, nose, and determine when each reaches full up or down. The motor is then controlled accordingly. There are safety systems to help prevent accidental actuation of the gear. A series of limit switches are needed to monitor the position of each gear during the operation of the system. A limit switch is simply a spring-loaded, momentary contact switch that is activated when a gear reaches its limit of travel. Typically, there are 6 limit switches located in the landing gear wheel wells. The 3 up limit switches are used to detect when the gear reaches the full retract, up, position. 3 down limit switches are used to detect when the gear reaches the full extended, down, position. Each of these switches is mechanically activated by a component of the landing gear assembly when the appropriate gear reaches a given limit. The landing gear system must also provide an indication to the pilot that the gear is in a safe position for landing. Many aircraft employ a series of 3 green lights when all 3 gears are down and locked in the landing position. These 3 lights are activated by the up and down limit switches found in the gear wheel well. A typical instrument panel showing the landing gear position switch and the 3 gears down indicators is shown in Figure 9.94. The hydraulic motor/pump assembly located in the upper left corner of Figure 9.95 is powered through either the up or down solenoids, top left. The solenoids are controlled by the gear selector switch, bottom left, and the 6 landing gear limit switches, located in the center of Figure 9.95. The 3 gear down indicators are individual green lights, center of Figure 9.95. Controlled by the 3 gear down switches. As each gear reaches its down position, the limit switch moves to the down position, and the light is illuminated. Figure 9.95 shows the landing gear in the full down position. It is always important to know gear position when reading landing gear electrical diagrams. Knowing gear position helps the technician to analyze the diagram and understand correct operation of the circuits. Another important concept is that more than one circuit is used to operate the landing gear. On this system, there is a low current control circuit fused at 5 amps, CB2, top right of Figure 9.95. End of page 9 to 51. This circuit is used for indicator lights and the control of the gear motor contactors. There is a separate circuit to power the gear motor fused at 30 amps, CB3, top right of figure 9.95. Since this circuit carries a large current flow, the wires would be as short as practical and carefully protected with rubber boots or nylon insulators. The following paragraphs describe current flow through the landing gear circuit as the system moves the gear up and down. Be sure to refer to figure 9.96 often during the following discussions. Figure 9.96 shows current flow when the gear is traveling to the extend down position. Current flow is highlighted in red for each description. End of page 9 to 52. To run the gear down motor, current must flow in the control circuit leaving CB2 through terminal 1 to the not down contacts of the down limit switches, through terminal 3, to the down solenoid positive terminal, upper left. The negative side of the down solenoid coil is connected to ground through the gear selector switch. Remember, the gear down switches are wired in parallel and activated when the gear reaches the full down position. All three gears must reach full down to shut off the gear down motor. Also note that the gear selector switch controls the negative side of the gear solenoids. The selector switch has independent control of the gear up and down motors through control of the ground circuit to both the up and down solenoids. When the landing gear control circuit is sending a positive voltage to the down solenoid, and the gear selector switch is sending negative voltage, the solenoid magnet is energized. When the gear down solenoid is energized, the high current gear motor circuit sends current from CB1 through the down solenoid contact points to the gear down motor. When the motor runs, the hydraulic pump produces pressure and the gear begins to move. When all three gears reach the down position, the gear down switches move to the down position, the three green lights illuminate, and the gear motor turns off, completing the gear down cycle. Figure 9.97 shows the landing gear electrical diagram with the current flow path shown in red as the gear moves to the retract, up, position. Starting in the top right corner of the diagram, current must flow through CB2 and the control circuit through terminal 1 to each of the three gear up switches. With the gear up switches in the not up position, current flows to terminal 2 and eventually through the squat switch to the up solenoid electromagnet coil. The up solenoid coil receives negative voltage through the gear selector switch. With the up solenoid coil activated, the up solenoid closes and power travels through the motor circuit. To power the motor, current leaves the bus through CB1 to the terminal at the down solenoid onward through the up solenoid to the up motor. Remember, current cannot travel through the down solenoid at this time since the down solenoid is not activated. As the up motor runs, each gear travels to the retract position. As this occurs, the gear up switches move from the not up position to the up position. When the last gear reaches up, the current no longer travels to terminal 2 and the gear motor turns off. It should be noted that similar to down, the gear switches are wired in parallel, which means the gear motor continues to run until all three gear reach the required position. During both the down and up cycles of the landing gear operation, current travels from the limit switches to terminal 2. From terminal 2, there is a current path through the gear selector switch to the gear unsafe light. If the gear selector disagrees with the current gear position, e.g., gear is down and pilot has selected up, the unsafe light is illuminated. The gear unsafe light is shown at the bottom of figure 9.96. The squat switch, shown mid-left of figure 9.96, is used to determine if the aircraft is on the ground or in flight. This switch is located on a landing gear strut. When the weight of the aircraft compresses the strut, the switch is activated and moved to the ground position. When the switch is in the ground position, the gear cannot be retracted and a warning horn sounds if the pilot selects gear up. The squat switch is sometimes referred to as the weight on wheel switch. A throttle switch is also used in conjunction with landing gear circuits on most aircraft. If the throttle is retarded, closed, beyond a certain point, the aircraft descends and eventually lands. Therefore, many manufacturers activate a throttle switch whenever engine power is reduced. If engine power is reduced too low, a warning horn sounds telling the pilot to lower the landing gear. Of course, this horn need not sound if the gear is already down or the pilot has selected the down position on the gear switch. This same horn also sounds if the aircraft is on the ground, and the gear handle is moved to the up position. Figure 9.96 shows the gear warning horn in the bottom left corner. AC supply. Many modern light aircraft employ a low-power AC electrical system. Commonly, the AC system is used to power certain instruments and some lighting that operate only using AC. The electroluminescent panel has become a popular lighting system for aircraft instrument panels and requires AC. Electroluminescent lighting is very efficient and lightweight, therefore, excellent for aircraft installations. The electroluminescent material is a paste-like substance that glows when supplied with a voltage. This material is typically molded into a plastic panel and used for lighting. A device called an inverter is used to supply AC when needed for light aircraft. Simply put, the inverter changes DC into AC. Two types of inverters may be found on aircraft: rotary inverters and static inverters. Rotary inverters are found only on older aircraft due to its poor reliability, excess weight, and inefficiency. The rotary inverters employ a DC motor that spins an AC generator. The unit is typically one unit and contains a voltage regulator circuit to ensure voltage stability. Most aircraft have a modern static inverter instead of a rotary inverter. Static inverters, as the name implies, contain no moving parts and use electronic circuitry to convert DC to AC. Figure 9.98 shows a static inverter. End of page 9 to 53. Whenever AC is used on light aircraft, a distribution circuit separated from the DC system must be employed. Figure 9.99. Some aircraft use an inverter power switch to control AC power. Many aircraft simply power the inverter whenever the DC bus is powered and no inverter power switch is needed. On complex aircraft, more than one inverter may be used to provide a backup AC power source. Many inverters also offer more than one voltage output. Two common voltages found on aircraft inverters are 26 VAC and 115 VAC. End of page 9 to 54. Light multi-engine aircraft. Multi-engine aircraft typically fly faster, higher, and farther than single-engine aircraft. Multi-engine aircraft are designed for added safety and redundancy and, therefore, often contain a more complex power distribution system when compared to light single-engine aircraft. With two engines, these aircraft can drive two alternators, or generators, that supply current to the various loads of the aircraft. The electrical distribution bus system is also divided into two or more systems. These bus systems are typically connected through a series of circuit protectors, diodes, and relays. End of page 9 to 55. The bus system is designed to create a power distribution system that is extremely reliable by supplying current to most loads through more than one source. Paralleling alternators or generators. Since two alternators, or generators, are used on twin-engine aircraft, it becomes vital to ensure both alternators share the electrical load equally. This process of equalizing alternator outputs is often called paralleling. In general, paralleling is a simple process when dealing with DC power systems found on light aircraft. If both alternators are connected to the same load bus and both alternators produce the same output voltage, the alternators share the load equally. Therefore, the paralleling systems must ensure both power producers maintain system voltage within a few tenths of a volt. For most twin-engine aircraft, the voltage would be between 26.5 volt and 28 volt DC with the alternators operating. A simple vibrating point system used for paralleling alternators is found in Figure 9.100. As can be seen in Figure 9.100. Both left and right voltage regulators contain a paralleling coil connected to the output of each alternator. This paralleling coil works in conjunction with the voltage coil of the regulator to ensure proper alternator output. The paralleling coils are wired in series between the output terminals of both alternators. Therefore, if the two alternators provide equal voltages, the paralleling coil has no effect. If one alternator has a higher voltage output, the paralleling coils create the appropriate magnetic force to open/close the contact points, controlling field current and control alternator output. Today's aircraft employ solid-state control circuits to ensure proper paralleling of the alternators. Older aircraft use vibrating point voltage regulators or carbon pile regulators to monitor and control alternator output. For the most part, all carbon pile regulators have been replaced except on historic aircraft. Many aircraft still maintain a vibrating point system, although these systems are no longer being used on contemporary aircraft. The different types of voltage regulators were described earlier in this chapter. Power distribution on multi-engine aircraft. The power distribution systems found on modern multi-engine aircraft contain several distribution points, buses, and a variety of control and protection components to ensure the reliability of electrical power. As aircraft employ more electronics to perform various tasks, the electrical power systems becomes more complex and more reliable. End of page 9 to 56. One means to increase reliability is to ensure more than one power source can be used to power any given load. Another important design concept is to supply critical electrical loads from more than one bus. Twin-engine aircraft, such as a typical corporate jet or commuter aircraft, have two DC generators. They also have multiple distribution buses fed from each generator. Figure 9.101 shows a simplified diagram of the power distribution system for a twin-engine turboprop aircraft. This aircraft contains two starter generator units used to start the engines and generate DC electrical power. The system is typically defined as a split-bus power distribution system since there is a left and right generator bus that shares, the electrical loads by connecting to each subbus through a diode and current limiter. The generators are operated in parallel and equally carry the loads. The primary power supply for this aircraft is DC, although small amounts of AC are supplied by two inverters. The aircraft diagram shows the AC power distribution at the top and mid-left side of the diagram. One inverter is used for main AC power and the second is operated in standby and ready as a backup. Both inverters produce 26-volt AC and 115-volt AC. There is an inverter select relay operated by a pilot-controlled switch used to choose which inverter is active. The hot battery bus, right side of figure 9.101, shows a direct connection to the aircraft battery. This bus is always hot if there is a charged battery in the aircraft. Items powered by this bus may include some basics like the entry door lighting and the aircraft clock, which should always have power available. Other items on this bus would be critical to flight safety, such as fire extinguishers, fuel shutoffs, and fuel pumps. During a massive system failure, the hot battery bus is the last bus on the aircraft that should fail. If the battery switch is closed and the battery relay activated, battery power is connected to the main battery bus and the isolation bus. The main battery bus carries current for engine starts and external power. So the main battery bus must be large enough to carry the heaviest current loads of the aircraft. It is logical to place this bus as close as practical to the battery and starters and to ensure the bus is well protected from shorts to ground. The isolation bus connects to the left and right buses and receives power whenever the main battery bus is energized. The isolation bus connects output of the left and right generators in parallel. The output of the two generators is then sent to the loads through additional buses. The generator buses are connected to the isolation bus through a fuse known as a current limiter. Current limiters are high amperage fuses that isolate buses if a short circuit occurs. There are several current limiters used in this system for protection between buses. End of page 9 to 57. As can be seen in figure 9.101, a current limiter symbol looks like two triangles pointed toward each other. The current limiter between the isolation bus and the main generator buses are rated at 325 amps and can only be replaced on the ground. Most current limiters are designed for ground replacement only and only after the malfunction that caused the excess current draw is repaired. The left and right DC generators are connected to their respective main generator buses. Each generator feeds its respective bus, and since the buses are connected under normal circumstances, the generators operate in parallel. End of page 9 to 58. Both generators feed all loads together. If one generator fails or a current limiter opens, the generators can operate independently. This design allows for redundancy in the event of failure and provides battery backup in the event of a dual generator failure. In the center of figure 9.101 are four dual-feed electrical buses. These buses are considered dual-feed since they receive power from both the left and right generator buses. If a fault occurs, either generator bus can power any or all loads on a dual-feed bus. During the design phase of the aircraft, the electrical loads must be evenly distributed between each of the dual-feed buses. It is also important to power redundant systems from different buses. For example, the pilot's windshield heat would be powered by a different bus from the one that powers the co-pilot's windshield heat. If one bus fails, at least one windshield heat continues to work properly, and the aircraft can be landed safely in icing conditions. Notice that the dual-feed buses are connected to the main generator buses through both a current limiter and a diode. Remember, a diode allows current flow in only one direction. Figure 9.102. The current can flow from the generator bus to the dual-feed bus, but the current cannot flow from the dual-fed bus to the main generator bus. The diode is placed in the circuit, so the main bus must be more positive than the sub-bus for current flow. This circuit also contains a current limiter and a circuit breaker. The circuit breaker is located on the flight deck and can be reset by the pilot. The current limiter can only be replaced on the ground by a technician. The circuit breaker is rated at a slightly lower current value than the current limiter, therefore, the circuit breaker should open if a current overload exists. If the circuit breaker fails to open, the current limiter provides backup protection and disconnects the circuit. Large multi-engine aircraft. Transport category aircraft typically carry hundreds of passengers and fly thousands of miles each trip. Therefore, large aircraft require extremely reliable power distribution systems that are computer-controlled. These aircraft have multiple power sources, AC generators, and a variety of distribution buses. A typical airliner contains 2 or more main AC generators driven by the aircraft turbine engines, as well as more than one backup AC generator. DC systems are also employed on large aircraft, and the ship's battery is used to supply emergency power in case of multiple failures. The AC generator, sometimes called an alternator, produces 3-phase 115-volt AC at 400 Hz. AC generators were discussed previously in this chapter. Since most modern transport category aircraft are designed with 2 engines, there are 2 main AC generators. The APU also drives an AC generator. This unit is available during flight if one of the main generators fails. The main and auxiliary generators are typically similar in output capacity and supply a maximum of 110 kVA, kVA. A 4th generator, driven by an emergency ram air turbine, is also available in the event the 2 main generators and 1 auxiliary generator fail. The emergency generator is typically smaller and produces less power. With 4 AC generators available on modern aircraft, it is highly unlikely that a complete power failure occurs. However, if all AC generators are lost, the aircraft battery will continue to supply DC electrical power to operate vital systems. AC power systems. Transport category aircraft use large amounts of electrical power for a variety of systems. Passenger comfort requires power for lighting, audio-visual systems, and galley power for food warmers and beverage coolers. A variety of electrical systems are required to fly the aircraft, such as flight control systems, electronic engine controls, communication, and navigation systems. The output capacity of one engine-driven AC generator can typically power all necessary electrical systems. A second engine-driven generator is operated during flight to share the electrical loads and provide redundancy. The complexity of multiple generators and a variety of distribution buses requires several control units to maintain a constant supply of safe electrical power. The AC electrical system must maintain a constant output of 115 to 120 volts at a frequency of 400 Hz, plus or minus 10%. End of page 9 to 59. The system must ensure power limits are not exceeded. AC generators are connected to the appropriate distribution buses at the appropriate time, and generators are in phase when needed. There is also the need to monitor and control any external power supplied to the aircraft, as well as control of all DC electrical power. 2 electronic line replaceable units are used to control the electrical power on a typical large aircraft. The Generator Control Unit, GCU, is used for control of AC generator functions, such as voltage regulation and frequency control. The Bus Power Control Unit, BPCU, is used to control the distribution of electrical power between the various distribution buses on the aircraft. The GCU and BPCU work together to control electrical power, detect faults, take corrective actions when needed, and report any defect to the pilots and the aircraft's central maintenance system. There is typically 1 GCU for each AC generator and at least 1 BPCU to control bus connections. These LRUs are located in the aircraft's electronics equipment bay and are designed for easy replacement. When the pilot calls for generator power by activating the generator control switch on the flight deck, the GCU monitors the system to ensure correct operation. If all systems are operating within limits, the GCU energizes the appropriate generator circuits and provides voltage regulation for the system. The GCU also monitors AC output to ensure a constant 400 Hz frequency. If the generator output is within limits, the GCU then connects the electrical power to the main generator bus through an electrical contactor, solenoid. These contactors are often called generator breakers, GB, since they break, open, or make, close, the main generator circuit. After generator power is available, the BPCU activates various contactors to distribute the electrical power. The BPCU monitors the complete electrical system and communicates with the GCU to ensure proper operation. The BPCU employs remote current sensors known as current transformers, CT, to monitor the system. Figure 9.103. A CT is an inductive unit that surrounds the main power cables of the electrical distribution system. As AC power flows through the main cables, the CT receives an induced voltage. The amount of CT voltage is directly related to the current flowing through the cable. The CT connects to the BPCU, which allows accurate current monitoring of the system. A typical aircraft employs several CTs throughout the electrical system. The BPCU is a dedicated computer that controls the electrical connections between the various distribution buses found on the aircraft. The BPCU uses contactors, solenoids, called bus tie breakers, BTB, for connection of various circuits. These BTBs open/close the connections between the buses as needed for system operation is called for by the pilots and the BPCU. This sounds like a simple task, yet to ensure proper operation under a variety of conditions, the bus system becomes very complex. There are three common types of distribution bus systems found on transport category aircraft: split bus, parallel bus, and split parallel. Split bus power distribution systems. Modern twin-engine aircraft, such as the Boeing 737, 757, 777, Airbus A300, A320, and A310, employ a split-bus power distribution system. During normal conditions, each engine-driven AC generator powers only one main AC bus. The buses are kept split from each other, and two generators can never power the same bus simultaneously. This is very important since the generator output current is not phase-regulated. If two out-of-phase generators were connected to the same bus, damage to the system would occur. The split bus system does allow both engine-driven generators to power any given bus, but not at the same time. Generators must remain isolated from each other to avoid damage. The GCUs in BPCU ensures proper generator operation and power distribution. On all modern split bus systems, the APU can be started and operated during flight. This allows the APU generator to provide backup power in the event of a main generator failure. A fourth emergency generator powered by the ram air turbine is also available if the other generators fail. The four AC generators are shown at the bottom of Figure 9.104. These generators are connected to their respective buses through the generator breakers. For example, Generator 1 sends current through GB1 to AC Bus 1. AC Bus 1 feeds a variety of primary electrical loads, and also feeds sub-buses that in turn power additional loads. End of page 9 to 60.